For all of human history, we've looked up at the Milky Way and seen a river of light stretched across the night. Beautiful, peaceful, eternal. We were wrong about all three. Between 2014 and 2022, a telescope named Gaia measured the positions and motions of 1.8 billion stars. Not just where they are, where they're going. How fast? In what direction? When scientists assembled the data into a 3D map, they didn't see a peaceful spiral. They saw a crime scene. Galaxies torn apart, stars fleeing in coordinated streams, and evidence of something massive, something we can't see, that crashed into the Milky Way 10 billion years ago. Its wreckage is still here. We're inside it. And until 8 years ago, we had no idea. Imagine trying to map a city from one street corner. No aerial view, no leaving. Just looking around and trying to figure out the layout from what you can see through the buildings. That's our situation with the Milky Way. We're inside it, about 26,000 light years from the center in one of the spiral arms. When we look at the night sky, we're looking through lanes of stars and dust, trying to reconstruct the shape of something we can never step outside of. For centuries, we couldn't even prove the Milky Way was a spiral. We just guessed based on other galaxies we could see edge on or face on. But there's a trick. Parallax. Hold your finger at arm's length. Close one eye, then the other. Your finger seems to jump against the background. That apparent shift lets you judge distance. Stars do the same thing. As Earth orbits the Sun, nearby stars appear to shift position against the distant background. The closer the star, the bigger the shift. Measure that tiny shift, sometimes less than 1,000th of a degree, and you can calculate distance. Do it for millions of stars, and you start building a 3D map. In 30 seconds, you'll see the machine that made this possible. The problem: most stars are so far away that their parallax is too small to measure from the ground. Atmospheric turbulence blurs everything. To map the galaxy, we needed to go to space. December 19, 2013. The European Space Agency launches Gaia, a spacecraft the size of a small truck, carrying 2 telescopes and the most precise camera array ever built. Destination: Lagrange Point 2, a gravitationally stable spot 1.5 million kilometers from Earth, where the spacecraft can orbit while staying fixed relative to the Sun and Earth. Out there, no atmosphere, no weather, perfect stillness. Gaia's job? Stare at the entire sky and measure the positions of stars with absurd precision. How precise? If you were standing in New York and could see a coin in Los Angeles, the width of that coin would be about 20 micro-arcseconds. Gaia measures star positions to within 24 micro-arcseconds. It can detect the width of a human hair from 1,000 kilometers away. Gaia doesn't point at one star. It spins slowly, one rotation every 6 hours, and as it spins, stars drift across its field of view. Each telescope has a focal plane covered in 106 CCDs, digital sensors. As stars cross, the CCDs measure position. Where is it now? Motion. Where is it going? Distance. Parallax shift over months. Color. What type of star is it? Radial velocity. Is it moving toward or away from us? Every star that crosses the field gets measured, then measured again 6 months later, and again. Over 5 years, Gaia observed each star an average of 70 times. That repetition is key. The more measurements, the more precise the parallax. The more precise the parallax, the better the 3D map. By 2022, Gaia had measured 1.8 billion stars. Not just positions, full 3D coordinates, velocities, and properties. That's roughly 1% of all stars in the Milky Way, which sounds small until you realize. We went from mapping a few 100,000 stars in 3D to nearly 2 billion. The dataset is 1 petabyte, equivalent to 20 million high-resolution photos. Just downloading it takes days. But when scientists started analyzing it, they saw something no one expected. The Milky Way wasn't just a spiral. It was a battlefield. First, the basics. Gaia confirmed we're a barred spiral galaxy, meaning the center isn't just a bulge of stars but an elongated bar, with spiral arms trailing from its ends. We live in the Orion Arm, sometimes called the Orion Spur, a minor arm between two major ones. The Sun orbits the galactic center at about 220 kilometers per second. One full orbit takes 230 million years. Since Earth formed, we've made about 20 trips around the galaxy. That's the simple part. Now look at the motion. If the Milky Way were a peaceful, settled spiral, stars should move in neat, circular orbits around the center, like a spinning disk. But they don't. There are regions where thousands of stars move together in the same direction, like schools of fish. There are stars orbiting backward, against the galactic rotation. There are clumps moving up and down, perpendicular to the disk. This isn't the motion of a calm galaxy that's been sitting peacefully for 13 billion years. This is the motion of wreckage. And that's when astronomers realized we weren't looking at a map. We were looking at a crime scene. Somewhere in the Milky Way's past, maybe multiple times, something violent happened. Galaxies collided, stars were torn from their homes, and the evidence is still here, written in the motion of billions of stars. Gaia didn't just give us a map, it gave us a time machine. And a mystery. What crashed into us? The first clue came from something called the Gaia sausage. In 2018, astronomers analyzing Gaia data noticed something odd. A group of stars in the halo, the diffuse sphere of stars surrounding the Milky Way's disk, had weird velocities. They weren't orbiting neatly. They were moving in highly elongated orbits, stretched into a sausage shape in velocity space. And they were old, metal poor, a different population from the Milky Way's native stars. Forensics. When a small galaxy collides with a large one, gravity doesn't smash them like billiard balls. It tears them. The small galaxy's stars get stretched into long streams. Some fall into the larger galaxy's center. Others get flung outward in elongated orbits. The original galaxy dissolves, but its stars remain, orbiting in a distinct pattern for billions of years. That's what the Gaia sausage is. The ghost of a galaxy. It was a dwarf galaxy, about 1/4 the mass of the Milky Way. Around 10 billion years ago, it fell into us. The collision dumped billions of stars into the halo and thickened the Milky Way's disk. Astronomers named it Gaia-Enceladus, after the giant from Greek mythology who was buried under Mount Etna. Fitting, since this galaxy is buried in ours. But here's the eerie part. We're not just looking at wreckage. We're inside it. Some of those stars, the ones torn from the dwarf galaxy 10 billion years ago, are in our neighborhood. We can see them at night. Some might even be the closest stars to the Sun. A galaxy died. We absorbed its corpse. And we didn't know until 2018. And it's not the only one. Gaia found debris from at least 5 other dwarf galaxies that fell into the Milky Way and were torn apart. Sagittarius dwarf, currently being consumed, stars stretched in a stream wrapping around the galaxy. Helmi stream Sequoia, even older than Gaia-Enceladus. The Milky Way isn't a serene spiral that formed peacefully and stayed calm. It's a cannibal. It eats smaller galaxies and grows. Most large galaxies do this. But Gaia let us see it, forensically, for the first time in our own galaxy. Now zoom in. Forget the whole galaxy. Look at our local neighborhood, within a few thousand light years of the Sun. Gaia didn't just map stars. It mapped the gas clouds where stars are born. And it found something no one predicted. A structure called the Radcliffe wave. A chain of gas clouds and star-forming regions, stretching 9,000 light years across the sky, oscillating above and below the galactic plane like a sine wave. And we're inside it. For 150 years, astronomers thought these nearby star-forming regions were part of the Gould Belt, a ring of young stars tilted relative to the Milky Way's disk. Gaia proved that wrong. There's no ring. It's a wave. A ripple in the gas distribution, oscillating with a period of about 200 million years. But what caused it? 3 possibilities. Supernova shockwaves from massive stars exploding in the past, spiral arm passage. Our region recently passed through a spiral arm, compressing gas. Bar resonance. The galactic bar's gravity creates waves in the disk. We don't know yet. But Gaia proved the structure exists, and we're inside it, literally swimming through a wave in the galaxy's gas. The Sun isn't in a star-forming region now. We're in a relatively clear bubble. But the wave passes through our neighborhood. In the past, the solar system might have been closer to these dense clouds. Some astronomers think encounters with dense gas, like edges of the Radcliffe wave, could have influenced Earth's climate over millions of years. Compressed gas means more cosmic rays. More cosmic rays might seed clouds. More clouds change albedo. Speculative, but intriguing. The structure of the galaxy around us might have nudged the history of life on Earth. Here's another revelation. Stars born in the same cloud don't stay together. Most stars form in clusters, gravitationally bound groups of hundreds or thousands of siblings. But over time, the cluster evaporates. Stars drift apart. Within a few 100 million years, the cluster dissolves, and its members scatter across the galaxy. Gaia can track them. By measuring velocities and rewinding the orbits, Gaia identified stars that are now thousands of light years apart, but were born together billions of years ago. They're siblings, separated by time and galactic motion, but chemically identical, like twins raised apart. The Sun formed 4.6 billion years ago in a cluster of several thousand stars. Within 100 million years, that cluster dispersed. Where are the Sun's siblings now? We don't know. They've scattered across the galaxy. Some might be in the halo. Some might have left the Milky Way entirely. But Gaia gives us a chance to find them. By comparing chemical compositions and rewinding orbits, astronomers are searching for stars that match the Sun's birth signature. A few candidates exist, stars with similar ages, similar compositions, and orbits that intersect with the Sun's birth location 4.6 billion years ago. Imagine, somewhere out there, a star that formed in the same cloud as the Sun, possibly with planets, possibly with life that shares a common origin with ours. Finding the Sun's siblings isn't just curiosity. It's finding family. This is the new field, Galactic Archaeology. Gaia turned the Milky Way into a time capsule. Every star is a fossil, a record of where it came from, when it formed, and what happened to it. By measuring 1.8 billion stars, we can rewind the galaxy's history. We can identify which stars came from which dwarf galaxies. We can reconstruct the timeline of mergers. We can trace the Milky Way's growth from a small disk 13 billion years ago to the massive spiral it is today. We're not just mapping the present, we're reading the past. And the story is violent, chaotic, beautiful. The Milky Way isn't unusual. Look at other spiral galaxies and deep images, and you'll see the same signs. Tidal streams, ribbons of stars torn from satellite galaxies, stellar shells, faint ripples in the halo from past collisions, thickened disks, evidence of mergers that stirred things up, spirals that look calm and symmetric from far away, reveal their scars up close. Galaxy formation is violent. Small galaxies merge into larger ones eat smaller neighbors. Over billions of years, this builds the massive galaxies we see today. The Milky Way is a survivor, and a cannibal. And the violence isn't over. In about 4.5 billion years, the Milky Way will collide with Andromeda, our nearest large neighbor, currently 2.5 million light-years away and approaching at 110 kilometers per second. The collision will take hundreds of millions of years. Stars won't actually hit each other. Space is too empty. But gravitational forces will fling stars into new orbits. The disks will be destroyed. Eventually, the two spirals will merge into one giant elliptical galaxy. Astronomers call it Milkomeda. The Sun will survive, possibly ejected into the halo, possibly flung into intergalactic space, but almost certainly not destroyed. One more thing Gaia revealed: dark matter's fingerprints. The Milky Way is embedded in a massive halo of dark matter, invisible, detectable only by gravity. That dark matter outweighs all the stars, gas and dust by at least 10 to 1. Gaia can't see dark matter directly, but it can see how dark matter's gravity affects star motions. By measuring how stars move in the outer halo, Gaia helped constrain the shape and mass of the dark matter halo. It's more spherical than we thought, more massive in the outskirts. And it's what holds the Milky Way together, the scaffold on which everything else hangs. We're not just inside a galaxy. We're inside an invisible gravitational cage made of something we can't see, don't understand, and outweighs everything we can see. Gaia's mission officially ended in 2024, but scientists are still analyzing the data. Data Release 4 is coming in 2025, with even more stars, better parallaxes, and refined velocities. The spacecraft collected data for over 10 years. That longer baseline means better parallax precision, distances accurate to within 1% for millions of stars. Each new release reveals more streams, more merger remnants, more mysteries. What's next in galactic archaeology? 1. Hypervelocity stars. Stars moving so fast they'll escape the galaxy. Where did they come from? What flung them out? 2. Dark matter subhalos. Clumps of dark matter orbiting in the halo. Gaia can't see them, but it can see gaps in stellar streams where a dark clump passed through and gravitationally disrupted the stream. 3. The oldest stars. Metal-free stars from the first generation after the Big Bang. If any survived, they're hiding in the halo. Gaia can find them. 4. Stellar nurseries. Where is star formation happening now? Gaia maps the gas, the young stars, and the feedback that shapes the next generation. And here's the beautiful part. Gaia's data is public. Anyone can download it. Anyone can analyze it. Citizen scientists have discovered stellar streams, identified unusual stars, and contributed to the map. You don't need a PhD to explore 1.8 billion stars. You just need curiosity. The galaxy is open source. We started with a question. What does the Milky Way really look like? Gaia gave us the answer, and it's not what we expected. We're not in a serene spiral that formed peacefully and stayed calm for 13 billion years. We're in a battlefield, a graveyard, a survivor. We've eaten at least 5 dwarf galaxies. Their stars are still here, orbiting in streams and shells. We're inside a wave of gas that's been oscillating for hundreds of millions of years. Stars born together are now scattered across the galaxy, and in 4.5 billion years will collide with Andromeda and become something new. For all of human history, we looked at the Milky Way and saw stillness, a fixed river of stars. Gaia showed us motion, chaos, history, violence, but also resilience. The galaxy survives its collisions. It grows. It makes new stars from the wreckage of old ones. And those violent collisions, the ones that tore galaxies apart and scattered stars, might be why we're here. Mergers compress gas. Compressed gas makes stars. New stars make planets. And one of those planets made us. We are the children of galactic crimes. The Milky Way isn't a map. It's a story. And Gaia let us read it for the first time. This is Cosmic Canvas, where the universe isn't just studied, it's painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.